our pleasure to have you here, sir. Welcome to our STTP on disaster management and resilience building. Hello, sir. Good afternoon.
Good afternoon.
So, welcome to our training, and we are all very excited to hear from you. So, I will invite Vivek. I will invite Vinay Nimbalkar to have your brief introduction to our participants, and then sir, you can start. Thank you. Vinay.
Thank you, ma'am. Am I audible to everyone? Hello, a very good afternoon to all, and dear respected sir. I, Vinay Limbarkar, on behalf of the Applied Mechanics Department and Engineering Ahmedabad and the Government Engineering College Modasha, welcome you all for the second session of the second day of this 5-day short-term training program on the disaster management and the resilience building conducted under the aegis of the Directorate of the Technical Education in collaboration with the Gujarat Institute of Disaster Management, Gandhinagar. With due respect, I would like to introduce you all a wonderful personality we are having today with us, Professor Dr. Arindam Dey, sir, who is presently an associate professor in the Department of Civil Engineering at IIT Guwahati and an adjunct faculty at the Center for Disaster Management and the Research at Institute of Technology. Sir holds a bachelor degree in the civil from Jadavpur University, Kolkata, and holds a master degree and the PhD degree in the geotechnical engineering from the IIT Kanpur. Sir has published many articles, reports, and books in his name. And Sir has also been a part of the many international and the national conferences. Sir is a reviewer of over 50 journal publications and a peer reviewer in over 10 journals. And Sir is directed more than 20 PhD students and more than 60 PG and the BTech students for research projects. Sir has contributing author for Technology of Home, which is a joint initiative by the JK Cement and the Association for Infrastructure Industry. Sir is also the member of the expert committee for the capacity building and the training on the geospatial science and the technology of the National Geospatial Program of DSTGOI from 2021 for 3 years. Sir also received IGS Soil Tech IG Award for the best paper on the Cello Foundation for 2017. Sir, I duly apologize if I have missed out on your important achievements and the awards, as there were so many of them. Now, without ado, I would like to welcome Dr. Arindam Dey, sir, and request him to grace us with his limitless knowledge and the experience on the seismic stability issues, investigation, mitigation. Over to you, sir.
Okay, thank you for a very generous introduction, Mr. Vinay. And first of all, I would like to render my thanks to Professor Rawal and other members who have invited me for this particular session. And okay, I think some echo is coming from somebody. Okay. So thanks to the organizers, and definitely I appreciate the entire initiative taken for this 1-week online training program for disaster building, disaster management and resilient building. And just to mention, I do not have any limitless knowledge or anything. It is very limited knowledge that we all have, and we just all, like all the students now also, we strive hard to gain more and more knowledge. And just whatever we have learned over the past few years, so I'll just try to be brief and give you the overview. So since this is for the short-term training and not definitely a classroom lecture, so we will not go into very much details of each and everything, but the intention is to make aware that if somebody is working or somebody is on the field related to this particular aspect of slope stability and mainly in the seismic aspects, so at least what all the things we should keep in our mind and then work forward. So with that brief note, and again thanks to the organizers, let me share my screen and start the session. Okay. Okay, let me know if you are able to see my screen.
Yes.
Is my okay? Okay, great. Okay, then with this note, let us start for this particular session. As already mentioned, I will be talking about the seismic slope instability. And in this regard, we will have a discussion on some of the aspects of analysis. How do we do the analysis for seismic cases, especially? And we cannot evade the topics of monitoring, because all our analysis depends on how good we monitor and collect the data. And then definitely a little bit about the mitigation, which may progress from seismic to aseismic conditions as well. So we will discuss this particular topic in a few phases. So the first phase, I will be discussing a little bit about the brief overview of the slope instability, just to tune up the audience for this particular session. So slope stability, as you know, this topic is nothing new. It has been practiced from ages in the natural slopes, but every day we keep learning. We are facing more and more difficult times due to this climate change and geological changes, which is occurring all around. And we start developing new ideas and new frameworks and more deeper understanding in this topic. Apart from natural hill slopes which are present in our country, in the world, so we have evolved from that. We create many artificially engineered slopes as well. Now, in the artificially engineered slopes, we create from our side, so we have more control on the creations, but still it faces the same wrath of slope instability due to various reasons. And when we talk about the reasons or the causes how the slope can fail, so we may have the causes as natural, so which may be related to the rainfall, precipitation, earthquake, volcanic activities, or we play spoil sport as human beings as well. We start cutting the slopes, excavating the slopes without understanding the implications. And you are very well aware that in most of the hilly terrains now, too much of urbanization has been in the impetus, and many constructions are being made in a reckless fashion without any engineering or semi-engineered ideas. To just give some glimpse of the beautiful natural slopes which we have. So these slopes are basically created in the geological past when the land rose due to the tectonic movements. They may be barren, they may be covered with green vegetations, and these are the ones which are ever present in our system from the prehistoric times. But as I was mentioning, over the times, we, in order to survive the nature, and then again, because of our readiness to grab more and more lands, we create many type of artificially engineered slopes as well. So these type of slopes are mainly restrained, or they are attempted to protect themselves from failure. But again, as I was mentioning, so slope stability and instability analysis forms an integral part of these engineered slopes as well. Just to show some example, they can be in the form of embankments and fills. The embankments may be used by the highways or the railways. We have many landfill waste contaminant systems where we have these artificial slopes, and earthen dams and levees to protect us from the riverine progression into the habitated areas. Then we have cut slopes, mostly in the hilly terrains, where we cut the slope or excavate the slope for the constructions or for the benching of the slope so that the disaster can be tackled. We have these cap and liner system for the landfills. And nowadays we go for protected slopes as well. So we have retained slopes. It might be retained with soil nails, or it might be retained with a mechanically stabilized earth retention system. However, since all these are slopes, ultimately always there is the paucity of failure, and then we need to analyze them properly. To give a brief notification about what do we understand by slope instabilities and landslides, this is a very legendary definition by Cruden which actually encompasses everything. So anything which is moving, it may be soil mass, it may be rock mass or debris. And if it is moving down a slope, we tackle with the problem of slope stability. Now, this can occur under natural scenarios in the hill slopes. It can occur in the river banks, and it can even occur below the water level. So submarine landslides are also common. It may occur due to some natural causes. There might be gully erosion due to heavy rainfall, or it may occur due to poor road construction and infrastructure practices. They may occur in soil, they may occur in rock, they may occur in the submerged strata. So the slope instability and landslide basically encompasses various types of geomaterials, various reasons for which they are dislodged. Just to see, in this particular case, we have different types of classification of slope instabilities, and the first type of classification is based on their type of failure. Now, this classification again subclasses the material composition. So the classification is based on rock or earth or debris, when rock, earth and water gets mixed together. And then it is classified in the types of movement. It may be a rock fall, earth fall, it may be a topple, it may be a slide. The slide again may be a translational slide in a single direction. It may be a rotational slide forming a circular or non-circular slip medium. It may be spreads and flows. Now, depending upon the amount of moisture which is present in the slope, so we move from the direction of falls to flows. So more the moisture, more the water content in the material, the stability or instability generated will be more towards the flows. However, in our natural analysis techniques or conventional analysis techniques, what we have, we try to classify these variations and do an independent analysis for each of them to study the instability. But the problem in the field is much more complex. So many of these may combine together. There might be combinations in the material properties due to the different materials getting mixed together, or there may be combination in the type of movement. So a slide can occur with a flow. Sometimes the rock fall is then followed by a subsequent debris movement, which may be a slide. So these becomes much more complex scenario in the field. Now, this is the most common type of classification. The other classification, which is coming up more and more in terms of the disaster and disaster management related issues, is the velocity of movement. Now, if there might be a slope failure, but if the velocity is extremely less, so you have ample time to provide protection or make some mitigation strategies. And a very low pace movement is mostly imperceptible. So it does not really create that havoc or panic or devastation if there is a failure under very slow to slow conditions. The problem happens when the pace of movement or the velocity of failure increases from moderate rapid to very rapid or extremely rapid. So higher the velocity, catastrophes are more if it is basically in an habitated area or if the road or railway networks pass through them. So depending upon the velocity, the destructive significances are observed. And nowadays, to basically cater or manage the disaster, we adopt many type of mitigation techniques or pre-mitigation evacuation plans, urban planning, and these are all now related to this velocity of the slope movement. So when we look into the slope instability, so we have two terminologies which come into picture. One is cause of instability and one is the instability trigger. So the causal factors are basically those factors which try to convert a stable slope and make it marginally stable. So the causal factors may not really lead to the sudden slope failure. So it will gradually convert the stability to lower and lower magnitudes, and it will just make the slope ready to fail. So it is just on the verge of stability, and that we call as a marginally stable slope. And then there will be some triggering factors, some single event that finally leads to the failure of the slope. So whenever we see any slope instability, landslide, slope failure, we should always remember that the particular event which led to the failure, let us say there is a heavy rainfall, and after the rainfall there is a landslide. So that rainfall will act as a trigger, but that may not be the only cause of that slope failure. Earlier, that particular triggering rainfall, there might have been rainfall continuing for a week, or there might be some toe excavation which has been done. So those might have changed the scenario of stability, and those are the causal factors. So when we look into the causal factors of landslide, there might be myriads of causal factors. Many of them are natural and many of them are man-made. Among the natural, we have geological causes, which relates to the weathering of the material or the natural fabric and structure of the material in the slopes. We may have morphological causes. The topography, a slope may be very steep or it may be flat. Steeper slopes will have more tendency to fail under distressing conditions. What is the surface cover, whether it is barren, whether it is vegetated, slope inclinations, whether significant erosion takes place at the bottom of the slope or in the channels in between the ridges, and whether there is any deposition or there is any tectonic activity which has slowly rendered the instability in the slope. Hydrological causes are one of the most important, one of the prime and one of the significant reasons. Rainfall, runoff, how much water is percolating inside the medium, how much water is flowing through the subsurface, the seepage conditions. And with the climate change occurring, the scenarios of geoclimatic changes becoming more and more harsh, these hydrological causes are playing much of spoil sport nowadays. Rainfall induced landslides have actually superseded the seismicity induced landslides. So rainfall induced landslides have become more frequent, but seismicity induced landslides are much more devastating in the case that a sudden release of energy actually dislodges a huge mass of land. And then we humans are there always to disturb nature in every form possible. We cut down the trees, we deforest, we cut down the hill slopes in an unscientific manner, not thinking whether the cutting will lead to any distress. We encroach upon the hill slopes. Probably it is necessary for some urbanization, but then it should be in a planned manner. And once we urbanize the area, we are never bothered about the drainage, the sewerage system. We construct roads in all unplanned manner possible. So artificial causes or these man-made anthropogenic causes play a big spoil sport in these instability conditions. And as I was mentioning, there are triggers. In general, we consider three important triggers. One is rainfall, one is seismicity, and one is the toe cutting. So especially due to the ongoing construction of infrastructures and road and railway networks in the hill slope. Rainfall may be heavy or it may be prolonged. If it is very heavy, occurring over a short interval of time, so high intensity leads to heavy erosion and then dislodgement. And if the rainfall is much prolonged, lot of water goes inside the slope, reducing the strength of the slope and thereby leading it to fail. In this particular discussion, we will little bit focus more on the seismicity part, how the seismic shaking results in the instability, how it increases the pore water pressure, and then how do we analyze those conditions in a simplistic or in a complicated way. Just to show or apprise ourselves some typical examples of seismic slope stability. One of the most infamous cult example is the Varunavat Parvat landslide, which occurred in 2003 due to the seismic event at that particular time. The green area, which was previously existing, had been more and more encroached by the habitations, and then mining started taking place. So already the thing was disturbed. There were causes of disturbances. And then one fine day when the earthquake event occurred, you can see the material started dislodging from the top, and there are two channels which are formed over this particular area. And this red dotted line which you are seeing here is basically the extent over which the devastation occurred. Some examples from Northeast, which is the most which is one of the most seismically active regions in the country. And every year we experience a lot of loss in lives, property, hill slope movement, damages, devastations in this area. These are some of the pictures which were taken by us for various instances. The seismic events can dislodge the rocks from the top of the hills if the composition is mostly rocky. And this is one such picture when we move from Guwahati to Shillong through the GS road. So many rock slopes also can be found. And this is one such picture when the rock mass dislodged from the top and fell on the adjacent road. And this is not a very uncommon scenario in these roads. Many times we want to protect the slope for some construction activities, but then many times our protection itself goes faulty. This is one such example where we were involved for a project in Mizoram. The hydropower plant was coming up, the slope was excavated, it was properly benched, no doubt, but then the entire slope was covered with concrete, shotcrete, the term which we use. So the slope was covered with shotcrete for a temporary protection measure, and then later it would have been renovated. But then what happened behind this slope face, a lot of seepage channels were there, water started accumulating, and one fine day when a magnitude of 4 earthquake, not very big, a magnitude of 4 earthquake occurred. Due to that earthquake, the pore pressure got generated from the backside, and then it bursted out the shotcrete and the entire slope over this range fell. So you can see the small truck and you can then understand the magnitude of the failure. Faulty constructions, as I was mentioning, was one of the prime reason, again, very near to our campus in the North Guwahati region. So there have been some excavations where excavations led to a very steep slope. Now each slope has their own angle of repose or inclination until which it can sustain the material. Now the slope was made steep, it was still sustaining, but again a small earthquake of 3.7 around magnitude again led to the collapse of this complete slope along with the constructions which was there. So all these basically lead to these seismic slope instabilities, some natural, some man-made conditions, and some just due to faulty engineering. So when we look into the slope instability studies, one major component that we basically try to focus is modeling and analysis of the slope so that we can prepare ourselves in conditions that if our analysis results show an impending failure, we can start taking protection measures, analyze them, and implement it on the field. But this particular modeling or analysis, whatever we do, is very much dependent on the parameters we get from the field investigation or laboratory investigations. Unless we get the proper parameters, we use them properly in the modeling may be done, but it might end up in estimating anything in a wrong manner, which probably would not help us further. So a big role is played by in situ and laboratory investigation, where we try to see what type of soil material is there, what is their strength behavior, what is their deformation behavior, how much water it can sustain, what are the various layers present in the slope in the form of stratigraphy. But in such slope instability studies, it is just not enough that you find out the parameter in one particular time instance. You also need to monitor whether there is any movement, any change of the scenario which might lead to slope instability. So monitoring becomes a very important part as well. So we try to monitor the displacement, we try to see whether there is any pore water pressure developing within the slope. And then we club all these things into proper modeling. And then based on the modeling, we go ahead with some mitigation measures as and when necessary. So then in the next phase, so that being the brief basics of slope stability, then let us now have a brief overview of the slope stability analysis. What are the various ways or techniques we use? Before going into the analysis, we should understand that there are two classes, broad classes of slopes, which we consider. One is infinite and one is finite. As the name suggests, the infinite slopes are those in a qualitative manner which extends over long distances and very large heights. So whenever we come to the Himalayan or the Deccan or the Ghats region, so basically we experience the natural infinite slopes. So this is one such picture from the Ramche area in Nepal, where landslide occurred in the natural infinite slope itself. Now, in these infinite slopes, the landslide or the instability occurs in a bit different way than what we see in our regular small scale landslides. So whenever the slope is infinite, so let us say this is the Ramche, Nepal area where infinite slopes, you can see it is more or less a constant or a uniform inclination and extending over a very large region. So in this case, what happens if any instability occurs, some part of the slope material starts moving in a slow pace or maybe in a moderate pace, but within shallow depths. And this type of failure we call as translational because it moves only in one direction and a major movement takes place over the extent of the area. It is shallow, so the depth of movement is not much. So we call them as translational shallow slip analysis for infinite slopes. What we do to show a schematic representation, so this upper line is representing the original surface or ground surface of the slope, and then probably up to some shallow depth there will be soil mass which is moving in the direction of the slope itself in a paced manner or in a slow manner. This depth of movement is not that great, so that's where we come to translational analysis. For the finite slopes, again, as we mentioned, that these are basically local scale slopes which are bounded by surfaces in the finite measurable dimensions. So all the artificially engineered slopes are finite slopes. The naturally occurring hill slopes may also be finite. When we bench the slope, when we cut the slopes at various locations, we create finite slopes in an infinite medium. So in the finite slopes or in the finite conditions, wherever we have bounding surfaces, so the failure pattern is bit again different. So in this case, the slope stability analysis, we may have to consider rotational slips. For example, if we have a slope which has a base and a crest, and there is no hard stratum at the bottom of the base of the slope, then the circular or non-circular rotational slip surfaces may develop. However, if there is a hard strata or a rigid stratum beneath the slope, the complete development of the rotational failure mechanism with circular or non-circular surface might not develop. And in this case, we get some compound slip surface because of the presence of rigid base stratum. So depending upon the material of the slope, what it is composed of, and whether there is some rigid stratum at the base or not at different depths from the base, so we may have various types of failure surfaces. If the slope is made up of much stiffer type of material, we may have planar failure surface as well, which is following only one particular line. If there are multiple layers of soil in the slope, we may have a two-wedge failure surface. So one planar up to here and then another planar surface, depending upon the two different type of stiff material comprising the slope. And as mentioned, we may have these circular, non-circular failure surfaces, and maybe it in a pure form or in a compounded form, depending upon the absence or presence of the hard stratum beneath the base. When we look into the analysis of these finite slopes, so finite slope stability analysis, there are various methods to do that. One very common method is called as the limit equilibrium method. As the name suggests, we try to find out the equilibrium condition in the limiting state for these type of analysis. So we try to find out the equilibrium of forces, equilibrium of moments, or equilibrium of both forces and moments. However, these limit equilibrium methods, although very popular, very quickly it will give you some result, yet it will not talk about deformation. It will not tell, from this analysis, we cannot tell how much deformation will take in a slope when it is failing. So for that, we need to move on to the next type of analysis where we combine stresses and deformation. We analyze through continuum-based modeling. Again, various techniques are there. We can use finite element, we can use finite difference, bounding element, meshless methods, and many other techniques have come up over the time. If we encounter rock is a bit different member of this particular family because rocks generally come with joints. And because of the presence of joints, we adapt different other techniques as method of wedges or the discontinuum methods, especially to cater the fact that pieces of rock can fall as chunks and get dislodged from the parent material. So the limit equilibrium or stress deformation does not really do cater that type of dislodgement, which can be tackled through methods of wedges or discontinuum methods, such as the discrete element or the distinct element methods. Some softwares are provided here just for the interested members. So if you are trying to do some slope stability analysis, these are some of the softwares which you can refer to. Now, just to mention, most of these softwares are commercial. It comes with a good price, but then always you will get the demo versions of the software. And if you want to do some basic analysis, you pick up any one of them, read about them, and use them. I should just caution, you should never use them blindly. You should first understand the basics and then use them so that you are more confident and your results are more reliable. So in the limit equilibrium method, as I was mentioning, this is a family of methods actually. So it can be used for infinite slope stability models or finite slope stability models. Finite slope stability can be affected or can be introduced in various methods. Friction circle, there are various types of methods of slices. I'll not go into the details of each of these, but just to give an overview, what does limit equilibrium do? If we basically have a slope and we have some mass or mass of the material which is trying to move away from its initial position, so it is trying to fail along the direction downward, so the part of the material which is trying to move generates a driving force. So it generates the forces or moments of instability, and there will be a chunk of material towards the bottom of the toe or the bottom of the slope, so which will try to resist the movement of the driving mass. So there is always a fight between this driving force and the resisting force. And if the driving force supersedes the resisting forces, so then the instability occurs and mass movement occurs. And if the resisting force doesn't allow the driving force to exceed, so then it remains stable. So this driving force and the resisting force are all generated at the interfaces of the moving mass and the mass of the soil or the rock which is not moving. So along this interface, we develop or we get the development of friction resistances or cohesion resistances, and this interface is basically called the failure surface, the one which we were describing earlier. So whatever instability is occurring is basically occurring above this particular failure surface, and within this failure surface or at this interface, the resisting forces and the driving forces keep on fighting with each other. So qualitatively, I mentioned that it is a fight between resisting and driving force and who exceeds whom. Quantitatively, we represent mostly or commonly in terms of factor of safety. So driving force basically represents the stresses which are developed within the medium. Resisting force are indicator of its strength. So factor of safety is basically a representation of the ratio of strength and stress developed due to the driving forces. And understandably, if strength is more, that is factor of safety is greater than 1, the slope is stable. If the strength is less, stress developed exceeds the strength, the slope fails. And then there is a condition where strength might be just equal or just up and down the stress developed. So that is a condition when factor of safety becomes nearly equal to 1, and we call it as a incipient failure. This physics of this problem is nothing new. Every one of us have read in the class 10, 12 school or college physics, and it is all dependent upon the friction concept which comes from the interaction of bodies. So if we have a mass which is resting over a frictional surface, and if we are trying to give a force, we will see that until the force exceeds certain particular value, the body doesn't move. And once it exceeds that, the body starts moving. And from that, we figure out what is the friction factor. And basically, this F1, which is the force which is trying to move the body, is nothing but which is represented as the stress developed or the driving force. And the frictional force in this particular case is the resisting force. So whatever we learned in physics is basically related to the frictional resistance. However, in soil, we have another component where the particles basically try to develop a bond between them. They shake hands with each other and doesn't want to move away. And that is what is referred as cohesion. So in any slip surfaces, whether it is a planar one, whether it is a circular one, a non-circular one, both frictional resistance and cohesive resistance will take part in defining the strength of the medium. So factor of safety is a conglomerated representation of the cohesive and frictional resistances to the stress developed from the driving mass. Now coming to this seismic part, so whatever I was mentioning up until this slide was under the static condition. So there is no external seismic forces. But when the seismic forces comes into picture, the basic concept does not change. Again, it still remains as a ratio of strength and stress. But then what changes is that the strength also gets affected by the seismicity induced as well as the stress which gets developed. So we are more keen to find out how much of stress is developed due to the seismic action, and then whether the enhanced stress is resisted by the strength or not. So again, we will resort to factor of safety. Now we need to calculate the stress, what is developed because of the seismic or the dynamic actions. So when we come to seismic slope stability analysis, this analysis can be carried out in different forms. One of the simplest form is pseudostatic. The next complex form is pseudodynamic, and next the most complicated form is dynamic. Now I'm saying simplistic and complicated, but I should frankly say that I should not use those words. So pseudostatic is basically a simpler representation of a complex problem, and it depends whether you will do a pseudostatic or a dynamic analysis. It depends on how rigorously or how efficiently you want to use the result and for what purpose you need those results. So depending upon your requirement, we choose these various analysis. So we will just have a glimpse and overview of these particular type of analysis, what we need to do and what we should keep in mind. Again, I will not go into details of each of these because each of these can be a discussion for 3-4 hours as well. So in pseudostatic, as the name suggests, we still do a static analysis, but the word pseudo comes into picture because we incorporate the seismic motions or the seismic vibrations in such a manner that we use some additional forces, but which are constant. Now we understand when we talk about dynamics or seismicity, it is a time-dependent phenomenon, but we tweak with the time-dependent phenomenon in such a way we give or use some acceleration coefficients, horizontal and vertical acceleration coefficients, and we consider them as constant and add up over the weight of the system and then do the analysis. So we have additional forces of kVW. So in the vertical direction, apart from the W or the weight of the system, we have another additional force kVW, and we have a horizontal thrust kHW. That all depends upon these two factors, kH and kV. That means in pseudostatic, we are not considering any time dependence. We are still in a time independent characteristic, and as well, we do not consider any amplification. When vibrations propagate from bottom to the top of a structure or any structure or the hill slopes or the dams and embankment, the upper portions get shaken higher and higher. So always it amplifies as it moves from bottom to top. But in this pseudostatic analysis, we neglect that amplification as well. So it is basically a static analysis, except that we add two extra forces somehow representing the seismic motion. How it is done, that I will show in the next ones. So this is a very simplistic analysis. We all are aware that we have seismic zones in India. In different regions, we have different levels of seismicity, and our IS code 1893 has given us some seismic zones. Now, seismic zones evolve with time. In 1966, we had a different seismic zone configuration. It changed over the time due to the changing tectonicity and the severity of the earthquake which started occurring in the various parts of India. And then currently we have this 4-zone map, zone 2, 3, 4, and 5, and where we broadly classify our country in these zones depending upon the severity of the earthquake. So the first way of finding out why I'm telling this, so this is one of the ways of assessing that two constants kH and kV, which we had used or which I had mentioned to be used in pseudostatic analysis. So based on these zones itself, we can do some understanding. So IS 1893 gives a very nicely decorated expression where we can find out the design horizontal seismic coefficient kH. So this is the coefficient for finding out the horizontal lateral thrust due to the seismic action without any time dependence. This equation many of you have seen, Z by 2, I by R, and SA by G. So Z is basically the zone factor. the zones which we are deciding in this entire region. I is the importance factor. It depends upon how important it is your structure. R is the response reduction factor, which basically talks about the condition whether your structure is rigid, brittle, or whether it is a flexible one. This factor 2 helps us reduce the zone factor from a maximum credible earthquake condition to a design basis earthquake condition. Maximum credible earthquake is the condition where the maximum force would be generated by the severe most earthquake in a particular region. But that severe most earthquake does not conquer or recur very easily. They take long return period to recur. So if you want to design by MC based condition, you will be ending up with huge structures, huge material, a huge volume of material, which is not desirable. So design basis earthquake, we decide that, okay, 2 or 2.5, which has been modified in the latest version, this particular factor decides that we reduce the severity condition so that our design can sustain for the next 30, 40, 50 years. And then SA by G, it is related to spectral acceleration. So not going into much depth of that. So if we know these values, in most of the cases in the common systems, I by R is considered as 1, SA by G is also considered as 1. But only in the common systems. If it is not so common, we need to evaluate these values. So in the common systems, what is done is that KH factor, that is the horizontal coefficient, is considered as Z by 2. And for each of these seismic zones in our latest condition, we have the zone factor given in the IS code. So given the zone factor, divide by 2, you get KH, and KV in general is half of KH. So we get KV as 0.5 KH. Now, once we know the magnitude of KH and KV, in the downward direction, we multiply with KV times the weight of the system. In the lateral direction, we get KH times the weight of the system. And based on these additional weights, we again carry out the static analysis. But when we look into this estimation of KH and KV through these seismic zones, one thing we understand that this is a very crude and broad classification. So for conventional classification, it is fine. But what happens is that all these zonations in the country is done in a macro scale, where it is mentioned that entire Northeast, for example, is in zone 5. But if it would have been actually so, if any earthquake would have been occurred, every place in Northeast would have experienced the same shake and same shock wave propagating. But it is not so. And that is because in these macro zonation models, we do not consider the subsoil layer, soil profile. So macro zonation is not a site-specific factor. That means the KH and KV, which you assess from this macro zonation, is more conservative. And for that purpose, we do a analysis which is called as site-specific ground response analysis. We locate, we set up our study area at various locations. We find out the subsoil profile and do the ground response analysis to figure out what is the exact amplification and acceleration at the surface due to the local subsoil present. And that will differ from your basic conventional macrozonation condition. And based on this site-specific ground response analysis, we, for each region, we figure out what is the distribution of the acceleration. For example, what you are seeing here is done by one of my MTech students earlier. So this is the city of Guwahati, the premise of Guwahati, and this more the red color, higher is the acceleration, bluish is the color, the lesser is the acceleration. So we can understand that just within the front area of Guwahati city of a 36 kilometer square area, if we build something in this red zone, we have to take higher values of KH and KV. If we build something in this blue zone, we have to take lower values. However, conventionally, we would have supposedly taken KH as Z by 2 and KV as 0.5 KH. We would have ended in a lot of over-safe and over-conservative design. Now, so as I was mentioning, what we do, so for static condition, we have the weight of the driving mass which is acting. And for the seismicity condition, we simply add the KH times W and KV times W in addition over and above what is the actual weight already acting over the system. So in case we have these accelerogram records. So what is accelerogram record? In many places, we have these accelerometers installed. And whenever an earthquake shaking takes place, it records the intensity, or it records basically the acceleration. So y-axis is the acceleration, positive and negative, and x-axis is the time. So these are some acceleration records. In general, the accelerometers come with a tri-directional sensor. There will be two horizontal, one in east-west and one in north-south, and there will be one vertical sensor. So from this particular scenario, if we do not want, or if we want to have more rigorous understanding about the kh kV values at a particular location where, let us say by chance an accelerometer is there, instead of going to all those zone factors, microzone, macrozone, we can take the acceleration record, find out the maximum value of the acceleration, and based on the maximum value, we can find out kh and kV. So we find out the acceleration in certain magnitudes, whether in centimeter per second square or meter per second square, divide by the parameter g, acceleration due to gravity. Whatever number we end up with, we get kh and kV. So sometimes the acceleration sensor can have only one horizontal direction. We simply use that value. If it has two horizontal sensors in a crisscross direction, we find out the resultant horizontal acceleration and use it in the same manner as shown in this equation. Sometimes we do not have a vertical sensor attached. If we do not have, we find out kh through the horizontal sensors and use kh by 2. If we have a vertical record also sensor available, we use AV max, that is the maximum of the vertical divided by acceleration due to gravity. But in this way, what we are basically doing, we are converting the time-dependent series to a time-independent parameter. However, there are certain concerns about that when we convert it into a time-independent parameter, so the energy from the pseudostatic condition, what we consider on a slope or any structure, is much, much higher than what is the actual dynamic energy imparted. So whatever design we do through pseudostatic analysis is still an over-conservative design. So there are concerns that if we use the peak values from horizontal or vertical records, we may end up with structures which may be massive, which may, let us say if it is an RCC concrete structure, it will have a lot of concrete. Some say it is fine, we are tackling the energy of the entire dynamic motion. But in other way, if you think, if you have a very massive concrete structure, it is more moving towards the brittle side. So the earthquake can actually generate cracks within the structure, and that also we don't want. So a concept has come over the time of effective acceleration. So where people says that we will not use the peak value, especially for the shock records which have single peak, you can understand that this occurs for a fraction of a second, whereas the actual energy is much lower. So if we design through this peak value, we are actually designing against much more higher magnitude of energies, which actually is not occurring. So we've tried to find out effective acceleration from certain time durations. Now, these are single peak amplitudes, single cycle peak amplitudes. We may have some earthquake records which have multiple peaks. That means the highest peak or the peak magnitude is basically getting closer with the available magnitudes at the other time instances. So that means whenever the peak magnitude comes with the enclosure to the effective acceleration magnitude, the devastation is much more. So multiple cycle peak amplitudes have much more devastation. But then confrontation came from few that how much or what should be the magnitude of effective acceleration, because it depends on the time duration over which you are analyzing the data. Now, always remember that your accelerometer or the accelerogram record, whatever time duration you are seeing here, is the time until which the record has been taken by the instrument. But the actual energy of the earthquake might be somewhere in a much lesser time, and beyond that there is no energy of the earthquake. So it is very important that we find effective acceleration. We need to also find the significant duration of the earthquake within which the energy is concentrated. So in that way, the concept of estimating the magnitude of effective acceleration came into being through some standardizations of time duration. So we want to find the bracketed duration. What is bracketed duration? So this is that duration of within the earthquake record when the significant energy can be associated with that particular earthquake. So different models came up to figure out what way we can find out the bracketed duration. So there are two main deciding criteria. One is related to threshold energy, and one again, other one is also with energy, but a central 90% energy tendency content. So what is the threshold energy concept? So if we look into any common accelerogram, this is a record from an accelerometer after the earthquake has taken place. You will always find in the accelerogram there is certain portion which doesn't show energy at the beginning. So it starts with a noise, that is the background noise. Then the earthquake kicks in. So you will have quite a bit of shocks up and down. And then after some time, when the actual earthquake motion has passed, the remnant of that motion will be there, which is again merging with the background noise. So your accelerometer might have recorded from 0 to t, that is the entire duration of record, but the actual earthquake might have occurred in a much lesser time within that record. Our duty is to find out that significant time duration. So one of the very simplest proposition which has been given by one of the professors, Professor Bolt in 69, is that you use an energy threshold content. So you have the accelerometer, you decide some energy threshold content. In general, it is decided as 0.05 times the acceleration due to gravity. You devise two lines, one above 0, one below 0, and find out the time between the first and the last exceedance of this energy. So as mentioned at the beginning, the earthquake has noise and then it picks up. So for the first time when the energy has been exceeded, so that becomes the first exceedance point. And then as the earthquake actual shock has moved away and then it is returning to the noise level, we find out for the last point where the energy level is exceeded. And this time duration becomes the bracketed duration. Now, there were concerns that it is still qualitative because somebody may say it's 0.05, it's 0.06. Sometimes we may not be able to properly recognize. So in that case, Trifunak and Brady came up with a more scientific approach called as the central 90% energy content. So it is basically stating that the actual earthquake energy is contained within the time interval between the points which signifies the initial 5% energy and the later 95% energy. So to show such an example, so we have this earthquake record. This is recorded by the accelerometer for 55 seconds, the Kern County motion. So what we need to follow a few simple steps. We have acceleration versus time, acceleration in y, time in x. So we basically make a modified plot. So what is that plot? First, we redefine this particular acceleration time record. We redefine this record as square of acceleration versus time. And then we make a plot of cumulative of the square of acceleration versus time. Now, cumulative of the square of acceleration is basically an indirect indicator of the energy of the earthquake. Once we have this plot, the topmost point we designate as 100% energy, that is based on whatever record we have, and then we demarcate. So wherever it cuts the y-axis, so we now divide from 0 to that particular point in equal 100 divisions. And then we also find out the 5% energy based on that discretization which we have made, and 95% of energy. So 95% line is this line which corresponds to certain time, and 5% is the small line at the bottom again which corresponds to certain time, 3.72 seconds and 32.44. And then the duration between this 5% and 95% becomes the bracketed duration. So you can see that the recording was for 55 seconds, but actual earthquake shock occurred only in 29 seconds alone. Now, this duration will be further used to find out the effective acceleration. So within this duration, you average out all the acceleration in their modulus form, and you get the effective acceleration, which definitely will be much lesser depending upon the single cycle or multiple cycle peak magnitudes. Then somebody told that, no, that is also not enough. That is too much of work to be done. We need some simplistic approaches as well, but still conforming to a more realistic scenario. So the concept of sustained acceleration and sustained velocity came into picture. The name suggests sustained. So we considered that if the absolute magnitude of acceleration, so that absolute magnitude of acceleration which is getting repeated either for 3 cycles or 5 cycles. And why some people are more fond of these SMA and SMV is that the more number of repetitions or cycles of earthquake motion our structures are impending upon, so the damage is more. So this is getting related to the damage incurred by the structure. So if we again look to those two examples, the Stone Canyon and the Koina earthquake. So Stone Canyon and Koina earthquake, more or less, their peak horizontal acceleration were the same. But if we look into the sustained maximum acceleration for 3-cycle repetition, so we see that 3-cycle SMA of Koina is much greater than 3-cycle of Stone Canyon. That means this earthquake is much more damaging than the Stone Canyon, although there is a sharp rise in the peak at one particular instant. Now, let us say you don't have accelerometer, you don't have much access to the codal provisions, then whether you will not be able to find out KH and KV, you still will be able to find out KH and KV. Now, whenever we have any earthquake, we get isosysmal maps. So we get the earthquake intensity distribution map from various agencies, USGS or PASMOS. What is isosysm? So these are lines of equal intensity. And again, our beloved researchers Trifunak and Brady from Long actually had investigated these isosysmal maps, and they gave us a relationship between the intensity of the earthquake in modified Mercalli scale to the acceleration magnitude. So with the help of isosysmal map, if you can find out what is the intensity of earthquake at different locations, and corresponding, you can find out the acceleration and use these expressions to find out KH and KV. Here it is just analogically written as AV and AH. So that is same as KV and KH. However, we should remember again, these are crude because at different areas, it will not be the same acceleration because of the local site effect. But it is always a good way to start the process. So finally, ending up that if you are working with pseudostatic accelerations, the analysis is same as the static one, that same slip circle and all those things, but you have to assess properly these two factors, KH and KV, horizontal earthquake acceleration coefficient and vertical acceleration coefficient. If you follow your code, if you know the zone factor, simply do KH as Z by 2 and KV as KH by 2. If you have a time history record from an accelerometer, if they're available, from the accelerometer record, you find out either the peak acceleration or the sustained acceleration or the effective acceleration based on the discussions we had in the previous slides, and find out KH and KV. If you don't have acceleration records, you don't have a code, you look into the internet, you find the USGS or PASMOS website for any earthquake, find out the isosysmal map, figure out what is the modified Mercalli intensity that will be also provided in the information, use these expressions to start with for the case of understanding KV and KH. So two important issues when we do this analysis for pseudostatic slope stability. Until now, I was mentioning that once you find KV and KH, rest of the part is simple, but two important things you need to always keep in mind. That whatever KV and KH you are finding out, there might be differences in opinion. So you and your friend might not agree to the same value of KH and KV because of different approaches. So in that particular case, when we do a pseudostatic slope stability analysis, we simply do not give a factor of safety. It's still the factor of safety, but we understand that factor of safety now varies with KH and KV. If there is a change in KH and KV, factor of safety varies. So we repeat these analyses. We can repeat because it is not that computationally expensive. It is less time consuming because finally it is a static analysis only. We repeat the analysis for various values of possible values of KH and KV for that particular locality or region. And then we give a graph where factor of safety varies with KH. And from that, we can understand that if there is a certain change in KH due to non-agreement between different persons, how much change in factor of safety will occur. So depending upon our design requirement, we follow this particular plot. One more important thing which we should always remember, which is a common mistake in such analysis, generally what we do, first of all, we do a static analysis. And then over the static analysis itself, you can see over the same slip mechanism, same slip surface, we add the horizontal and vertical additional forces due to earthquake and repeat the analysis. But that is not actually correct. What happens when the slope is present and if there is an earthquake motion, the slip surface or the failure surface which gets developed due to the earthquake motion is not the same as that of the static analysis. So when we do hand calculations, so we should remember that we need to take into account the new or the modified slip surface due to the pseudostatic condition. So if you are simply using the slip surface from the static condition, doing the pseudostatic analysis, probably, or in most of the cases, you are not actually ending up in a right result. So the critical surface for pseudostatic condition needs to be found out. So this exercise we had used in several projects. In one of the projects which we got from the PWD in Arunachal Pradesh. So in that the PWD approached us because of the road constructions which was ongoing in Arunachal Pradesh. Lot of hill cutting activities are going on. So they approached us to give them certain idea that whether the hill slope is inherently stable or whether it has any chance of jeopardy, and if they can do a slope cut, how much extent they can cut so that the roadway can be constructed without leading to the slope instability. So what we did, we simply did a pseudostatic analysis because we don't want to invest so much at that particular moment for full dynamic analysis. However, we took hydraulic conditions also. We took water conditions also in the analysis. And then we found out in stages that if it is a dry slope under static condition, what are the factor of safeties, if there is a water table, if it is a dry but under pseudostatic condition with earthquake forces in that particular region, and then all together what is the condition. And based on that, we provided some colored monograph that if we know the soil parameters, cohesion and friction in their combination with the water table condition, pseudostatic condition, or both, what is the status of the factor of safety. Wherever it is more than 1.2, we consider it to be safe, whereas all these colored numbers you can see are less than 1. That means the slope in those combinations of soil parameters would show instability in one form or the other. Then we extended that understanding to the position to find out how much of toe cutting can be done in these particular slopes. For example, I'm showing only one trivial example here. Let us say we are considering a slope having an inclination of 30 degrees. It is a frictional slope. Material parameter is 20 degrees. And then we induce, or we also have some cohesion in the slope. Now, when we see that under the dry static condition, if we see these particular lines, each of these lines are for various magnitudes of cohesion. So this particular line shows a slope with material cohesion as 70 kPa and friction angle as 20 degrees, whereas this particular line shows a cohesion of 10 kPa and 20 degrees. Obviously, cohesion, lesser cohesion means lesser stability of the slope. And if we draw a line factor of safety of 1.2, we can see that under the dry condition, a slope with 10 kPa cohesion can be cut up to the magnitude probably of 8 meters. Beyond that, if we extend the cut, the factor of safety decreases, the slope will move towards failure. And if it is a very stiffer slope of material cohesion as 70 kPa, we can even go up to a magnitude of cut of more than 30 meters, although that is very idealistic. When we add pseudostatic condition to that, interestingly, now you can see that even in the slope of having cohesion 30 kPa, we cannot do any vertical cut, any toe cut, because it is already below 1.2. It will move to the level of failure. So for C equal to 30 kPa, earlier we could have cut up to 20 meters for the dry region. For the pseudostatic condition, we cannot make any cut. And similarly, when it is wetted, we again can find out how much of toe cut we can do. So based on pseudostatic analysis, these beautiful representations can be made, and we can develop a very nice forefront idea about hill slope toe cuts for roadway construction without jeopardizing the hill slope. Now, does it mean that we cannot cut the C equal to 30 kPa slope? Let us say if we have a C equal to 30 kPa slope material and still we need to construct the road, we still need to cut, but we need to now give protections to prevent the slope from failing. So this approach helped us to understand without protection how much we can cut, and if we need to cut beyond that, beyond in certain material composition, whether we need protection or not. Now, that next level of little bit complicated analysis is what we call as pseudo-dynamic. Pseudo word is still there, but now it is more dynamic in the sense. Earlier case, I mentioned that we do not consider any amplification. In this case, we are still considering KH and KV. These again the pseudostatic coefficient itself are considered, but now we consider some amplification in KH and KV from bottom to top. So for earlier case, for the entire backfill or the slope material region, it was the same value of KH and KV. Now it varies from bottom to top. As it moves towards the top, the magnitudes of KH and KV increases. Now, how does it increase? Whether it is a linear increase, non-linear increase, that is a different discussion altogether. And we can find out from either field investigation or ground response analysis studies. Now, why is it actually needed, this amplification? As the wave starts moving from bottom to top, as you move towards the top, the soil confinement reduces and you get more and more displacement and more acceleration. And that's why this amplification is required. So that means depending upon how much or what is the pattern of amplification, now the factor of safety, the stresses, everything will start varying. So we go one step ahead to represent the failure characteristic, that we find out for different magnitudes of KH, first of all, what is the scenario of stresses, and then we find out the stress parameters with different amplification factors. So FA, what you are seeing in this equation, is the amplification factor which relates KH or KV at the bottom to the KH or KV at the top. FA may be linear one, or it may be a non-linear representation. And the last most important analysis, what we need in a most rigorous manner, is a dynamic analysis, which we also call as time history analysis. Time history means now everything is time dependent. We are not going to consider KH and KV. We are not going to consider any slip surface beforehand and do the analysis. So in time dependent time history dynamic analysis, everything will evolve. So for example, this is one such structural representation with a retaining wall and a backfill, and we induce the dynamic motion at the bottom. Now it is full dynamic motion. So so responses now will vary with time. In earlier cases, responses were never varying with time. It was varying with some other parameter. So when we do this analysis, and mostly we take help of the numerical tools, either finite element or finite difference or other type of continuum tools. So in these type of numerical investigation, we do not make any assumption. We do not take horizontal or vertical earthquake acceleration. Neither we prior decide what will be the slip surface or the failure mechanism. Everything evolves on its own. For example, here you are seeing some rock slopes. I will again show them later in another slide, where the failure mechanism is a complex failure mechanism, which is passing through different joints. So it is not really a circular or non-circular or a two-edge, bilinear, nothing like that. It is that plane which after analysis have shown particular failure. In these cases, some extra issues which come into picture for time history dynamic analysis, topographic amplification, that I will discuss later in another slide. The most important takeaway from this slide is that now whatever factor of safety you are finding out is no longer either a constant like the static or pseudostatic analysis, or it doesn't vary with the amplification factor. Rather, here the factor of safety keeps varying with time. And the main reason for that, because the stresses all along the slope, the stress developed, the driving force, the driving stresses which are developed along the slope are all varying with time. The earthquake motion is shaking the system, and the forces will go from positive to negative of different values, different shapes, different distributions at different instance of time. And that's why the factor of safety keeps varying with time. So in this type of time history dynamic analysis, as I was mentioning, it is quite rigorous. So again, different types of analysis are there. Equivalent linear is a bit simplistic analysis. Non-linear dynamic is the most complex one. But again, we should remember in this particular case, again, we have to find out certain parameters of soil. So here we find out dynamic parameters of soil. One of the most important is the modulus reduction parameter. What is modulus? So G represents the shear stiffness of the soil. Now we need to understand that as we keep on shaking the system, its strength or stiffness becomes lesser and lesser. And that's why through some experimental investigation, we need to find out with different strains, with number of cycles and number of strains, how does the strength or the stiffness of the system reduces. Because This reduction estimation is important because in the nonlinear dynamic time history analysis, the real or the most realistic representation comes into picture, that the forces, the driving forces keep on increasing, and along the same time, the strength also keeps on reducing, which was not available to assess in the earlier methods. Now, since both of them are changing, the actual analysis or the concept of analysis becomes more complex, and I am not going into that. So until now, whatever I was showing was like a section of a slope, and the same thing can be elaborated or enhanced to study in a 3D manner. Now we all understand whatever hill slopes, whatever finite slopes we look onto, they have a 3D structural representation. So whatever concept we develop in the sectional or 2D analysis until now, which we were discussing, can simply be expanded to 3D system. However, now the 3D system, since it is a more complicated representation, the number of forces, the entity, orientation, inclination for the 3D system variation, everything will increase. So it is just adding to the computational complexity, but the concept remains the same as we were discussing in the previous case. So as I was mentioning in all the earlier analyses where we were discussing about limit equilibrium, even in this particular 3D limit equilibrium condition, we only balance forces, moments, or both of them together. Neither of them would give us a deformation in the system. And that's where, as I mentioned earlier, we need to go to continuum or coupled stress deformation analysis. So where we model the system in finite element or finite difference or other techniques and run or execute the system based on some guiding, constitutive, or material behavior model. And here again, we do not need to assume anything. Everything evolves on their own. So for such an example, if you see this particular slope model here, you can see that the slip mechanism has started to develop. So this is for one particular time instance of the representation. This red colored considers a very less factor of safety. So the slip mechanism started to develop, yet it had not reached the top. That means this portion of the slope will start to move, and yet the top at this particular instant of time has not moved. So the mechanism started from bottom to top. Similarly, a mechanism may start from top to bottom if there is any movement. And along with that, we can find out the deformation contours and see how much of actual deformation is taking place in the slope. Now, why deformation is important? Many a times, if you are passing by a hill slope, you would not be really that feeling safe if you see a portion of the hill slope is actually hanging over you. Although the stress might not have exceeded the strength, it is still stable, but to just see a portion of the slope hanging over you sends a ring of panic through you that you are not safe there. And that's why this deformation based concept analysis is also important to understand how much of deformation would really lead to the actual instability or psychological instability of the system. And this analysis may come with or without pore water pressure, depending upon whether water is present in the slope or not. Just to give a glimpse of rock slope stability, which is a different type of member in our slope stability analysis. As I was mentioning, rocks come with joints. Now, depending upon the joint type, number of joints, spacing of joints, inclination of joints, whether it is inclined towards the face or towards the body, different type of failures also occurs in rock slope. And depending upon the earthquake motion guided by the joints, again, different type of failure and displacement movements can be noticed. So if there is only one set of joint, the rock slope may slide along that joint. For example, you can see a plane failure in this bottom right picture. If there are two sets of joints which are crisscrossing each other, a portion of the rock which is basically attached to these two sets of joints will come out. That is called a wedge mechanism. You can see this wedge failure in the bottommost right picture. If there are more number of joints, it can happen that pieces of rocks within that joint are starting to tumbling or toppling failure from getting dislodged and failure just by dislodgement. And if the joints are more and more, that means the rock becomes more and more fractured, we may even get circular type of failure surface as we are seeing in the rock, as we are seeing in the soil. So depending upon the type, configuration, and characteristics of the joints, we can have plain, wedge, circular, or toppling failure. And the earthquake motion will lead to such failures whenever these type of joint sets are prevalent. So there is a way to find out what type of failure will actually or possibly take place, which is through a kinematic analysis through the application of the stereo nets. I'm not going into the details of that. You can definitely search through stereo net keyword in your internet or in the books to get an idea how through very basic analysis we can tell whether if there are too many joints in the rock, whether the rock will fail by sliding, whether it will fail by wedge, or whether it will be like circular slip failure, and through which joint it will fail. So again, that is like a limit equilibrium analysis. We do not consider any deformation. So it will just tell whether or which type of failure will occur. But then we want more. So we want to understand along with the failure condition, if the earthquake motion is there, how much will be the deformation as well. So we, as earlier for the soil slope, here also we move to pseudostatic analysis. For example, this is one of our project at NH58 where there had been some partial failure. We investigated and found that there are 3 types of joints which are prevalent in the rock, and we could notice that mostly joint 1 and joint 2 and a partial failure of joint 3 is taking place. So we studied with the pseudostatic analysis, and then we could reach to some inferences, not going to the inferences, but interestingly what I wanted to show here, again through the continuum modeling, we are not assuming anything. So you can see that the failure line is developing here, and then whichever joint is weaker, through that joint the failure line is going. It is not even a 2-wedge planar failure type of system. So it is not a biplanar system. It is just a diffused system passing through the joints. So that means up to this level, probably there will be a linear movement of the slope, but detachment will take place through various joint sets here. And depending upon the magnitude of the pseudostatic motion, depending upon the earthquake in the regions, records, then we can do the analysis for various KH, KV values. And as earlier, we can represent factor of safety or strength reduction factor in terms of KH and KV. Now, when we do time history analysis, so this was pseudostatic, this is time history. Now, when you do this time history analysis, you get more and more information. So in the time history analysis, you can actually monitor in your analysis various points, how they're deforming, how much stress is developed, what is the displacement direction. So in one such analysis, this is a typical representation that after the rock slope has failed, you can see its new shape. And you can see that all these sharp edges have developed. That means through one of these primary joint, this joint J1, there are many joints at particular spacing. Each of the joints are actually moving out at certain location. But if you need to find out which joint is basically the culprit in leading the slope to failure, again, we need to monitor different points in the analysis itself. And through those points, depending upon the joint characteristic, we can find out the critical joint, which actually triggered the failure. And since it failed, the other joints over it started failing. We can also find out up to which point the joint failure has taken place, all through the monitoring of the horizontal and vertical displacements. So through these techniques, we can find out which is the critical joint, how much portion of the joint is failing, and how much deformation or displacement will be induced into the system. I told that I will talk about topographic amplification a little bit because it's a very, very important thing for a slope stability analysis, especially in rock and the stiffer soil slopes, in any C5 soil slopes actually. So what is amplification? Already we mentioned that as the earthquake motion passes from bottom to top, more and more acceleration generates. So when we look into a horizontal subsurface, this is not a slope, this is a plain ground horizontal subsurface, many layers of soil are there. Once it starts moving from bottom to top, we will see that more or less at different locations along the horizontal extent of the soil at different layers, more or less the PGA value remains the same, except some deviations here and there. More or less it remains the same along the horizontal distance. But as soon as we have undulations within the horizontal ground, so the ground surface is horizontal, but the internal layers, you can see the undulations here, and we repeat the same exercise, you will see the amplification or the PG actually moves up and down. That means these undulations are now playing a big role in changing the acceleration of the system, which is recorded at various locations along the same horizontal depth, along the same depth. And then based on different analysis, we could see that if there is undulation, if the system is not homogeneous, it is a heterogeneous subsurface with undulations, we can see that there is a lot of difference in the amplification. So you can see this green colored line is the 2D heterogeneous condition. This one, which is much different than this red colored line, which is the 2D homogeneous condition. So that means it is very important to understand the amplification not only because of wave or the shocks moving from bottom to top, but what are the undulations. Now imagine this thing going to the slope. So now the slope face is inclined and all the earthquake motions are coming from bottom to top. For example, if we consider this particular point, we will have direct incoming earthquake motion. Further, some motions will go to the face and they will get reflected towards this. That means in the horizontal ground level, whatever magnitude of acceleration this would have shown, in the sloping ground, this will show actually more amplification because of the presence of the slope face. Now imagine if there are many joints, if there are joints present. So at each joint, now coming to the basic refraction of waves, what we study in school physics. So that same refraction of waves will keep on taking place and new waves will be generated, which will start participating in increasing the acceleration. So wave directivity due to the slope faces or joints, wave generation due to the presence of joints at different locations. So they will all start playing in increasing the amplification at the top of the slope. That's what is called as topographic amplification. And any simple amplification is like what we have discussed for the horizontal ground. A very nice animated way to show this is that, let us say we have a slope. We did 2 boreholes. In one borehole, we kept the responder, or we kept a charge from where the waves will originate. In the other borehole, we have a transmitter, we have a receiver where the waves will be recorded. So if our intention would have been to record the direct wave from this to this particular receiver, this would have been our intention. But if due to the slope face which is nearby and the slope crest which is nearby, this action will generate waves from different directions which will be moving towards the receiver. So it may reflect from the face, it may go to the face, go to the crest and then reflect back, or it may go to the crest and reflect back. So that means whatever record we are getting here is a conglomeration of all the reflectances what is taking place, not only this black direct wave which has moved from this red point to the blue point. System becomes more complicated because of the human interventions. As I was mentioning, we do too much of urbanization, hill slope constructions, and now we have many structures over the hill slope. So already the hill slope was showing a lot of topographic amplification due to its terrain, topography, rocks, joints, everything. And now we have buildings. So we have a lot of foundation structures in the buildings. And when such system is affected by the earthquake, the concept remains the same. The response becomes more complicated. The buildings, the foundations, the adjacent buildings at different levels, everything start participating in modifying the response of the slope under the seismic or the earthquake conditions. If the footings are too closer, if you see the buildings are too closer, a failure mechanism can develop by conglomerating all the regions of this building. So this entire section can come down. If the footings are little bit far apart or the building loads are far apart, it may happen that only one of them get affected and not the other. So depending upon the seismic activity and their analysis, we can also decide in the hill slope how much interaction will be there between different buildings in case of a seismic activity. And by doing such analysis, we can actually plan the urbanization. But unfortunately, it is not done so, and we see a lot of devastations and catastrophes in the urbanized hill slopes when a seismic activity takes place. So these all I was talking in a local scale, some small region, but if you need to analyze the slope stability for a bigger region. So in this particular case, the major change, what happens is variability. Larger the region, your parameters start to vary. In a local scale, you take a single landslide, you do the stability analysis. But in a bigger region, you cannot go on doing the single landslide for every point of the region and stability analysis. And that too, you need the variability of the ambient conditions of the parameters. So when we do in a regional scale, we call this as susceptibility analysis, not really a factor of safety, but a probability of failure. We go to the probabilistic level. The main reason of doing that, just to show what can vary: rainfall, it can vary over space, it can vary over time, seasonal variation. Soil, subsurface soil profiles can vary tremendously when you move over the hilly terrains or the hilly slopy regions. Then in the hilly regions, you will have bedding plains, faults, folds, and that can again vary significantly, all due to the tectonic and rising of the hill slopes which have taken place in the prehistoric era. Soil property can vary, hydraulic characteristics can vary, geological and geomorphological characteristics can vary. So now if so much of the variations and variability is coming into picture, we cannot really do a simple slope stability analysis and find out factor of safety, because since things are varying, things are uncertain. So in that particular case, we bring probabilistic analysis into picture. I will not go into the depth or any detail of that. Just to mention, in this case, we do not take any single parameter value. So if we are taking soil property, for example, cohesion or friction, we will take a distribution of those properties. If we are taking the loads and the drainage condition, we'll take a distribution of that. So these distributions come from the probabilistic probability distribution functions, again, which depend upon a lot of investigation and experimentation. We fit all these distributions in a model, but now this model includes uncertainty. Now, if there is uncertainty in the input, there will be uncertainty in the output as well. So in the output, we no longer talk about a single factor of safety, but a probability of failure or the chances of failure over that region. And then how to find out the probability distribution function for each parameter, whether there is any relationship between the two parameters, cross correlations, all those need to be ascertained. Not going into any of those things. Just to show a very interesting thing, let us say we have one hill slope where we have done significant amount of investigation, and we found out the distribution of the soil parameters of C and phi within the hill slope. Now, depending upon the distributions what we are adapting, we may adapt some distribution where you can see the pockets of the parameters are developed. In one distribution, you can see more or less the pockets are developed in such a way that a layered arrangement can be seen. Same hill slope, with different distributions, we will get different instability response. So this failure of the hill slope will be different. So this gives us an idea that we need to work upon much on the investigation and finding out the distribution of the parameters over the hill slope. So spatial variability has to be taken care in a very conducive manner, in a very convincing manner, so that we get the real failure response of the slope. If we end up in wrong estimations, we will end up in wrong results. As simple as that. And obviously, this we have already talked about. We have variations in seismicity and local site effects. So coming to the last part of this discussion, that we do, as I was mentioning, we do all these analysis, but it all depends upon investigation and monitoring. So various types of investigation and monitoring we need to do to get to know the parameters, not only for one particular instance, but we need continuous monitoring or intermittent monitoring. One such monitoring which is definitely to be required in such slope stability analysis is mass movement monitoring. You can use EDM, you can use inclinometers within the slope. So as the slope moves, the inclinometers take different shapes, and from that you can find out how much of movement has taken place. You can use extensometers. Extensometers are what? In a simplistic way, if we tell, there will be two posts in which one wire will be connected. And as there will be movement, one of the posts will be moving in relative to the other, and the wire will be stretched or compressed. And based on those relative movement, we can find out how much of superficial movement is taking place. or there will be strain meters. You can see some strain meters is hanging from here. So extensometers are here. And then there can be ground tilt meters. Tilt meter shows how much is the tilting or rotation due to the mass movement of the soil. So mass movement monitoring can be done, and whatever is shown here, these are contact monitoring. That means you have to go to the site, install these instruments and monitor. Always not possible, especially in the natural hill slopes, it's very difficult. So that's where we resort to the aerial photographs, sat images, and we go with the advanced surveying techniques using GPS, and many times we use this time domain reflectometry as well. So time domain reflectometry helps us in understanding through which locations the critical slip surface has developed due to that particular movement which has occurred. So if we monitor aerial photographs over the time, we will see slowly the mass is shifting from one portion to the other, and that continuous monitoring will help us to understand what is the velocity of movement as well, which I mentioned as a very important factor. And this technique was actually used through LIDAR, where the velocity of soil movements was monitored. And this is an example of Pizzo d'Alvano in southern Italy, where due to this continuous geodetic survey and LIDAR-based technique, where the velocity and the direction of the movement, type of movement was recognized from a much ahead of much earlier time before the actual event. So many people were actually saved. This entire town of, or one portion of the town of Pizzo di Alvano was actually devastated, but evacuation was done much earlier. Interestingly, in this particular figure, you can see a red circle. So this is the hospital region which was not evacuated. They are so confident on their data, what they're monitoring, that they could find out which are the channels through which the landsliding will take place, and those channels were not in the hospital region. The hospital was not evacuated. So through these techniques, you can monitor the velocity of movement, the types, the extent of damage which can incur pre and post landslide or slope instability events. Water, definitely have to know about water. So we have a series of hydrogeological surveys, and we try to find out where is the water table, whether it is a continuous water table, how much moisture content is there, what is the degree of saturation, whether there is a parched water table, a localized water table if it is present, how much seepage is taking place. All these things are monitored and investigated. And for that, we have groundwater monitoring system. Two major instruments are piezometers. So once you install piezometers at different locations over the slope, you can figure out what is the groundwater table. But groundwater table, above the water table, due to the soil, capillarity occurs in the soil. So above the water table also there will be saturated zones. So those saturated zones can be figured out from the in situ tensiometers or DPS tensiometers. Different type of piezometers are there depending upon the requirement. It may be hydraulic, it may be pneumatic, it may be electric, but the purpose is still the same. We need to install it in a series and figure out what is the groundwater level. Lastly, you need to monitor rainfall very thoroughly. We have strain gauges deployed at various locations. So this will be strategically located strain gauges, not gain gauges. So we deploy them at various locations because, as I mentioned, that is one of the most variable parameter. But more relevant to our discussion is the deploying of the accelerometers and accelerographs at various locations, so that we can monitor the seismic event or the microseismic event at different locations. Monitoring at one station in Arunachal Pradesh might not help the effect to be recorded or effect to be affecting the locations in Assam. So we need seismic monitoring stations at different locations. We deploy them strategically. Then based on different types of collatory analysis, we bring the responses together and then figure out what will be the PGA and all those events or all those entities what we had discussed earlier. Last portion. Once we do all these things, finally, we should keep an eye a little bit on the mitigation techniques as well. As I mentioned earlier, always there is a fight between the driving force and the resisting force. So our mitigation objective is very simple: reduce the driving force or increase the resisting force, or both. Now, we have already understood that driving forces can get increased because of unstable grounds, water present in the system, and then we need to increase the resisting force by removing the water, removing the unstable ground, any weak surface, whatever is present, we can eliminate them, or in a different other alternative ways. One alternative way is basically unloading. Wherever there is a mass movement, go with a dredger and you remove that. You might have, you may experience when you travel in the steep hill slopes, many places where landslide take place, always a dredger goes beforehand to clear that and the traffic movement starts, and then the rest of the work starts for dressing and all the slopes. So remove the material or bench the slope strategically so that this benched slope is a slope with lesser inclinations, and these benches helps to prevent the movement of the soil in the localized zones. So these are some of the basic, this is one of the most basic technique. You can use buttressing, you can use rock buttressing at the toe of the slope. So it is like putting some wedges beneath the wheel of a car when it is standing on a sloping ground. That wedge will not allow the car to move. So in a similar analogy to this, various types of buttressing we have soil and rock fill, we can use shear keys, we can use MSE walls or the advanced geosynthetic based walls, and even indigenous techniques of using tires. Even vegetation is a good way to tackle the problem. Most important is drainage. You need to channelize water through the surface so that it percolates at least as possible, and whatever subsurface drainage is necessary to remove the water from within the slope material we have to do. And for that we can, for surface drain we can have concrete drain, ditch drain, catchment drains. For subsurface we can have the trenches, drain blankets, or perforated platy drains or horizontal drains installed. Main reason is that whenever seismic action takes place, the subsurface pore water pressure rises, strength decreases, and it leads to failure. So if you can remove water, the strength remains at that particular level what is desired. So removal of water is very important. In many hill slopes you might be seeing at different locations, the indigenous people actually put say half shredded bamboo within the hill slope. They use it for fetching the water, but although it is helping them apart from helping them with the water for their drinking purpose and other purposes, it is also releasing the water pressure from the hill slope within. So in a way, it is giving a stability to the hill slope as well. And then various types of external reinforcements, soil nailing, stone column, micropile, various types of reinforced retaining wall. This can be used in protection to the seismic induced failures. Now understand that the basic concept of analysis is still the same, whatever we discussed previously. Here some additional protection measures are coming, and these protection measures also need to be analyzed against the seismic forces. Again, these are some tieback walls, and as I was mentioning, vegetation over a geocell layout or a geosynthetic layout is another very fine way of approaching this stabilization problem. Shotcreting and other stabilizations are also available, biostabilization and shotcreting. But again, as I mentioned earlier, one such event, shotcreting has to be done very carefully with caution, and weep holes have to be left so that the shotcreting has some effectivity. Otherwise, it might lead to triggering of failure as well. So in a nutshell, these are some of the protection measures. If there is rockfall, you can have security or catch fences. Still, if there is a possibility of dislodgement, you can have the security drapery system. If the slope is steeper, the security drapery system will slide off, so you can protect it with soil nailing or rock bolting. You can have rockfall security embankment. If even some rocks fall down, they will fall behind this one. So these all are related to either seismic or aseismic dislodgements as well. Not going into the other ones, it is a different workout. Now, some pictures. This is from the Konkan Railway, the rockfall protection measure in the draperies which are installed. These are basically wire meshes anchored at different locations. Rockfall embankment, as I was showing, we create this embankment by the side of the road. Due to seismic activity, if there is some rockfall happening, rocks will come and get arrested behind this, and time to time they need to be dredged and removed. These are the hanger nets which I showed in that picture. These are used to arrest the rock at much higher levels than even coming down to the roads. So for rockfall barriers which are using these hanger nets, these are very high tensile wires which can catch the rocks, and proper tests and experimentations are done to decide how much tensile strength of the wire for different regions has to be. What is the strength of this post? Now, if there is some seismic activity which can lead to the breakage of the debris-induced dams in the hill slopes, then the huge mass of debris starts flowing. Now, debris is rock, soil, water, everything is coming into. Again, these debris barriers actually can help. They will arrest the debris behind the barriers. Water will pass away. Over the time, although they can get overloaded, the debris will start flowing. And in such a situation, we generally give a lot of series of debris barriers. And once the debris flow season is over, the debris which are collected behind the nets, they are dredged off, and these can be made reusable for the next time. And many a times we do not want to catch the rocks. We want to allow the rocks to fall off, but we need to protect the highways and sections through which the vehicles and people are passing. So we have these rock sheds and rock tunnels. So let us say this is a steep rock ridge, and if due to some seismic activity there is a dislodgement, so it will fall on these rock sheds and tunnels, and it will go to a downhill region where probably there is no jeopardy if the rock falls over the valley. So these are again used not to basically prevent the rock from falling, but channelizing the rock which is dislodged due to some seismic or aseismic activity to a downward region and keep the location workable. So to summarize and make some final remarks, what we discussed is basically about seismic slope stability with some aseismic components as well. And we can understand that it depends upon several factors: geometry, compositions, motion characteristic, if there are joints or beddings, amplification, water or hydrologic condition, spatial variability in the regional scale. And one thing is to be very clearly noted, that we need a lot of instrumentation and investigation and monitoring to decide for the in situ movements, in situ parameters, and then only we can go to a modeling aspect. So modeling aspect comes, or the success of the modeling aspect will depend how well you measure or how well you detect the scenarios. And then obviously, if you see that there are dangers, there are jeopardy impending, so you can go for various types of stabilization and mitigation measures. Again, these are site dependent. You need to decide which to choose, how to choose. So those are different topic of discussion. Lastly, this entire domain of slopes instability, landslides, whether it is due to seismicity or rainfall or aseismicity or any other condition anthropogenic, the solution to this is not a one-man show. So a lot of people have to come together with different types of expertise. Definitely geotechnological people has to be there, geologist has to be there, hydrologist, climatologist, they have to come and join hands, seismologist, especially in the seismicity induced landslides, earth science experts for the sat images and the aerial surveys. And most importantly, we need people from instrumentation, electronics, signal processing, transportation, who can join hands. And finally, all of them, when they put their brains together, probably then we can get a very sustainable hill slope practice. So before finishing, I would like to acknowledge my students who have worked a lot on these areas. Many of the slides I have taken from them with or without permission. I have learned a lot with partnering with my industry collaborators. Many of the pictures which you have seen here are actually provided by them. So I'm thankful to many of these industry partners and many more. And obviously all the researchers, field practitioners who are working day and night, putting their brains together to move towards a sustainable and betterment of the available or existing understanding. And lastly, thanks to the organizers to rope me in this particular event. And I really appreciate the gesture, and I hope I could convey some of the issues. Definitely, everything which I told has much bigger picture behind. But again, as I told earlier, this is only to make the audience aware of different scenarios, what they need to keep in mind for such seismic slope stability induced situations. So thank you for your patient hearing. I hope it was somewhat understandable. Only bit of knowledge what we could gather. Thank you all.
Thank you, sir. I would say it was an ocean. It is an ocean of that, and you have made us a journey and given us some glimpses of role of various disciplines can contribute to this sector. Further, I would like to say the way you have conveyed from scrap, considering all variety of disciplines of our participation, it has been a wonderful lecture to watch and digest, I would say. We will definitely try to contribute our bit in some of the area, and it is not a remote problem. It is like all over India problem if we think upon. So, sir, your lecture will definitely contribute to a lot. Thank you very much, sir.
Thank you.
Now I will open the session. It's open for interaction. Participants, you're welcome to ask questions or interact. Hello, sir.
Dr. Rawal, you are muted, I think. I see everyone is appreciating. Any questions from? Okay, then I have one thing to ask, sir. I've been to Himalayas, and Your voice is breaking. Your voice is breaking. Actually, not able to hear.
Am I audible now?
Better, but still breaking. Please continue.
Okay. Okay. So, yeah, am I audible properly, sir?
Yes, better, much better. Yes.
Okay. So when I had been through Himalayan mountain range, particularly Badri Kedar, so what I felt is the mountain is on verge of
I'm not able to hear it again. Got it severed the. Dr. Rawal, I'm not able to hear at all. So there is no audio coming this side.
No issue, sir. Sir, I had been through Himalayas, and what I felt at that time was the Badri Kedar mountain particularly is loosening up quite a bit. So is it under monitoring? Is it something going on?
Yes, some locations are definitely under monitoring, especially after the incident which took place, right? That Kedarnath incident which took place. So many agencies have stepped into some of the vulnerable regions are definitely under monitoring, but the main issue, what I have come to know from various agencies, that it is such a wide extent. Setting up monitoring stations at all the locations in the mountain range is difficult. First of all, accessibility and maintenance is another issue there. But many vulnerable regions where access is there, they have actually set up stations at least, and aerial survey is always being done. At least that monitoring is always there. So in that way, I should say continuous or semi-continuous intermittent monitoring is going on in those regions.
Because that we have a special Himalaya in India, and got a little bit concerned what will happen to our city. Okay. Thanks, sir. Thank you very much.
It is actually definitely in concern, sir.
and delivering such a good insight on slopes. It was a terrific journey on slopes. Like it was like a tip of an iceberg, but we were through in that. Thank you very much, sir. For your
Thank you.
expertise. Thank you.
Okay, thank you all. Thanks to all the audience for patiently listening. If you have any queries later on also, just you can find my contacts in the website, email, mobile numbers, everything is there. Always feel free to contact. You need not step back anytime from contacting.
Thank you.
Okay, thank you all.
Okay, thank you. Good day, sir.
Good day. Good day to you all.